So Jocelyn Bell Burnell, I met her actually. She's a fantastic lady, very funny, super approachable, and at the time, and the year was 1967, right? And that's when we discovered the first pulsar. Well, she discovered the first pulsar. Her supervisor got a Nobel Prize for it. A few years later, she didn't, which in my opinion is super unfair. She's very cool about it, though. She just kind of says that was the time, but I think she definitely should have gotten the Nobel Prize. The way it happened is very interesting as well, because so up until 1967, when she found the first pulsar, neutron stars were fully theoretical objects. And just to explain maybe what neutron stars are, first of all, for those who probably heard the name but don't really know what they are, I personally find them super fascinating. I know black holes are all over the place, and everybody loves.
I hope not.
But neutron stars are, as I think I mentioned in the beginning, right, that they are the densest matter that we can find in the universe. So like the final bus stop before the black hole. And they pop into existence after stars die, and not just any star, but very massive stars. So for example, our sun, when our sun will die, it will be actually quite boring, because what will happen, it will first, in the next 5 billion years or so, it will exhaust its nuclear fuel. When hydrogen nuclei basically fuse together, produce energy, that's why stars burn. That's why we see them in the sky. Well, once the nuclear fuel will be exhausted fully, then the star will, our sun will kind of swell up at first to become a red giant and eat up Mercury, Venus, and unfortunately Earth as well. We won't be there anymore, but very sad fate. And the outer layers of the sun will become just a planetary nebula, but the core of the sun will become this very small object called a white dwarf, which will be the size of the Earth, but very, very massive. So actually also quite massive, not as massive as neutron stars, but still, like, imagine the mass of the sun, you put it in the object the size of the Earth, and that's your white dwarf. White because it's very, very hot at first, so we see this white light kind of radiating, when it's super hot, then we can see the entire spectrum, all the colors as white light. And then with time, it will become black and fade into oblivion, and we will, become a black dwarf, and we will never be able to detect our sun ever again. So if we were to detect it from, somewhere else. So that's the fate of the sun, and rather boring death. But if you look at stars that are much more massive, more than 8 times more massive than the sun, to be specific, then once hydrogen fuel is exhausted, what happens is then when kind of these lighter atoms fuse together, they form heavier and heavier elements. So from hydrogen, we get helium. From helium, we get carbon. Then we get oxygen and, neon, magnesium, silicon, I think, afterwards. And finally, we get to iron. So all of this kind of, they fuse, they give off energy. The star continues to live. And then at some point, when it gets to iron, well, iron actually needs energy, and you cannot create energy by fusing iron nuclei. It doesn't happen. Iron is like the end point here of nuclear fusion. So what happens then, when the star is stable and you have this pressure from nuclear fusion counteracting the pressure of gravity, well, if you don't have fusion anymore, then basically gravity starts being the only energy source at this point. The core starts to shrink, and there's no more resistance to counteract the gravity, and everything just goes boom. So protons and electrons get squeezed together and become neutrons. So there are a lot of neutrons, and the resulting object is this core, which is the neutron star. We see the supernova explosion all around because it's we can detect it in optical, of course, and it's super, super bright, can outshine a galaxy. There are about, I think, 2 or 3 of these supernova explosions that take place kind of in 100 years or so in Milky Way alone. So stars die pretty frequently. The neutron star that stays behind is this fascinating tiny object of about 20 kilometers across. So if you imagine a city, I don't know, the size of Chicago or something, and you curl it up into a ball. And 20 kilometers across, and you put all the mass of the sun into that tiny sphere.
A sun massively bigger than our sun.
It could be 1 to 3 solar masses. That's the mass that could be shoved into a tiny 20-kilometer diameter sphere, which is a neutron star. Anything bigger and it will collapse into a black hole. So to remain stable, it has to have this very specific kind of mass. And it spins and it travels through space at high speed. So that's your neutron stars. And we didn't know they existed for real. They were theoretical for quite some time before Jocelyn discovered them. I think the first time they were theorized was in 1934 by Franz Zwicky and Walter Baade. And those two guys, they just kind of came up with this idea, very correct idea, that supernovae were due to stellar death and a neutron star would remain. But the problem was it was 1930s and, there were other problems at the time. So even Oppenheimer, he actually worked on neutron stars quite a bit before he got distracted by atomic bomb project and pulled in a totally different direction. He was the one who came up with the upper limit of the neutron star before it collapses into a black hole. So he did some really pretty important work. But still, it was, again, mathematical, theoretical. And then finally in 1967, back to Jocelyn, she was a PhD student in Cambridge working with her supervisor, Anthony Hewish, who was super passionate about discovering more quasars. Quasars are these active galactic nuclei that are super luminous objects in the sky, and they are powered by supermassive black holes inside galaxies. And we had just discovered them at the time, so everybody was like, wow, super cool, let's look for more. And that's what Jocelyn was doing. She was putting wooden poles into the ground and connecting them with copper wire to create this quite primitive-looking array. So an observatory made out of wooden poles and copper wire, effectively. I actually went there. It's still there. You can still see the wooden poles. Copper wire had been stolen and sold, unfortunately, but the wooden poles are still there. So anyway, she was looking through data one day and she was looking for these quasars, and suddenly she saw a very weird signal that was repeating, just a peak, and it was repeating a few times. And she thought, what is this? That's not a normal quasar signature. So she went to her supervisor, they examined it, and they thought those were aliens, like for real. They really thought for quite a few months that those were aliens signaling from somewhere in the galaxy, signaling the Earth. And they kept it super hush-hush. They didn't tell anybody about the discovery because she discovered 3 more. So she discovered 4 in total of this.
A lot of aliens, oh dear.
Yeah, exactly. And so they named them LGMs, little green men. So those were the names for the for the first signals that they got. And she was actually pretty upset. And when I was thinking about today's interview, today's podcast, I even bookmarked here in my book. I'm going to read you a short quote from her, because she said she was about to defend her PhD thesis in about 6 months or so at that time. And so she said, "Why would little green men be using a daft technique signaling to what was and probably still is a rather inconspicuous planet?" So that tells you about her sense of humor, but also, what she thought about the project at the time. But of course, it turned out to be not aliens, and they knew, so they just analyzed and reanalyzed the data. And finally, the paper was published in February 1968, and they said that it was indeed neutron stars. And that was just the bombshell discovery and beginning of pulsar astronomy. It was super cool.
All right, so what did we just watch right there?
We watched Thinking on Paper, bite-sized, a shot of technological tequila to your prefrontal cortex. It's just a taster, a smorgasbord of what awaits you with the full Thinking on Paper interviews. There really is nothing like it out there at the moment, connecting the dots of all these technologies. So subscribe where you're listening, check the long-former interviews out, and remember, stay curious.
Be disruptive.
Keep thinking on paper.